So one reason that this class is a prerequisite for other things like economics is because you can use optimization. So there's a couple types of optimization that we can talk about. So one is like global optimization. So this means like you want to find the maximum. Optimization just means finding the max and the min. So if it's global optimization, that just means what's the max and the min of the function over the entire space, like the entire real line. So if you have something like f of x equals 4 minus x squared, that looks like this. And you can, what's the max? Well, the max is 4. And what's the min? Well, there is no min if you're allowed all the values. The min doesn't exist. So this is, for global optimization, there is no minimum. It can just be anything. And so we'll do two-dimensional functions, so surfaces like over the entire plane. Sometimes they don't have a maximum because it just goes up, and sometimes they don't have a minimum because it just goes down. But in life, there are often constraints. So you want to learn absolutely as much multivariable calculus as you possibly can, but we're constrained by the fact that we have only about 3 months to do it. So you could have optimization on a constrained region. So in single variable calculus, that would mean like, suppose we want to maximize this function, but only on this little orange interval here. Well then, you can find it definitely has a max value, and it definitely has a min value. There they are. So it allows you to definitely have a max and a min anytime you have a constrained region. And in 2 dimensions, this is like we looked at Kansas. So Kansas looks something like this. So there was Kansas. And so this is our region, our constrained region, and we want to find the maximum and the minimum elevations in Kansas. So sitting above this is a function. So it looks maybe something like this. So there's the surface sitting above Kansas. And you found that the maximum was here, and maybe the minimum is like somewhere over here. So you can find the max and the min. And when you do this, as you discovered, you need to check for interior maxes and mins, because Kansas could have a mountain inside where the maximum occurs. It doesn't. You have to check the boundary, because there might be like a mountain right over here, and so the maximum is close on the boundary, and that's indeed what happens with Kansas. And you have to check the corners, because it could be that like its friend Colorado is very high, and so the closest point to Colorado is the highest. And that's not the case for Kansas, but it is a case for Nebraska. So you have to check this. So there's the 2 ways, global optimization and then optimization on a constrained region. And the last one is optimization under a constraint. So this is what happens in economics a lot. So you imagine that, for example, it's nice and warm out, and you have ice cream cones, and you have ice cream. The cones are just the cone thing. And so in economics, there's this concept of an indifference curve. So if you had like a lot of ice cream but no cones, you'd be a certain amount of happy, not that happy. If you had a lot of cones and no ice cream, you'd be not that happy. And if you had like a middling amount of both, that would make you like just as happy. So this is a curve along which you're like, kind of happy. But then if you have more of everything, you're like a bit more happy. And then if you have a lot of everything, you're like the most happy.
Whoa.
Super happy. And so then you want to buy ice cream and cones, but in your pocket, you only have such and such amount of money, which trades off between ice cream and cones. And so you have this thing called a budget constraint. And you want to be as far out as you can on these happiness curves. You don't want to do this one on the sad curve or this one on the sad curve. Sorry, you can't make it quite to this one, but you can make like one of these intermediate ones. And so it turns out that we want to find a point where these things are tangent. So this is what you figured out with the hike, that you want to find the place where things are tangent. See here you have like a lot of ice cream and one cone, so you can just put all your ice cream on your cone and be happy. So those are 3 kinds of optimization, and for this we use this awesome idea of Lagrange multipliers.
Oh.
It's the point. What are you saying? oh no, you should say, oh yay! Lagrange multipliers are like actually the coolest idea. And that's the idea that these things are tangent here. Alright, so those are the three kinds of optimization that we'll do.